In this video, we are going to be talking about representations of groups. So literally, we'll be representing. The molecule that we want to look at today is water. And for this particular molecule, we're going to use a slightly different set of axes. The horizontal axis is still going to be x, but we're going to set this axis to be the z-axis. On this board, then, coming out perpendicular to the board would be the y-axis. The reason for doing that, typically we like to have the z-axis coming out of the board and make the plane of the board the xy axis. We're not doing that in this case because for water we notice that the high order rotation axis goes along here. So we write it in this particular case for convenience so that we can draw water as a planar molecule, which it is, but also have the C2 conveniently to draw. So this is the high order rotation axis. We know, of course, also that for water it has the identity because every molecule has the identity. We have C2. And then we have two different mirror planes. One of the mirror planes is in the plane of the board. So since we have a planar molecule, there has to be a mirror plane. And that's in the xz plane. So we can write it this way as sigma xz. And the other mirror plane is going to be along this way, so perpendicular to the plane of the board, and that's going to be the yz plane. So we have these four symmetry operations in our group. So we recognize from work that we've done before that this gives us the point group C2V. So C2V is an important point group. It's very common, and it's the point group of the incredibly important compound water. So for this particular group, we have these four different symmetry operations. What we'd like to do now is to write out explicitly the matrix forms of these symmetry operations. And that's going to be a key idea in this video, this idea of representations of groups. Representations are matrix forms for the various symmetry operations. They can be 3x3 matrices, which is one we're going to see at the beginning, but they can also be 1x1 or 2x2 matrices. So it just has to be a matrix, not necessarily a 3x3 matrix. So for the identity, we recall that we can write it as just a series of ones along the diagonal, and all the other positions are going to have a value of 0. For C2, C2 is going to be rotating around the z-axis. The proper form for this is going to be -1, 0, 0, 0, -1, 0, 0, 0, 1. And we could have gotten that by substituting into the general formula for Cn, which tells us the cosines and sines of angles and such. Then the third matrix that we want to look at is sigma xz. And recall, it's kind of a shortcut that this tells us that the numbers along the row are going to be 1s for x and z, but it's going to be a -1 for y. So we have 1, 0, 0. Recall this is the x position. The y position is going to be a -1. And then the z position is again going to be a +1. So by knowing what mirror we have, we can write down the elements of the matrix directly. Last but not least, we have sigma yz. And here notice that y and z are explicitly mentioned. That means that the x is going to give us a -1, 0, 0, 0, 1, 0, 0, 0, 1. So we were able to write out the 3x3 matrix forms of each of the symmetry operations. And we're going to highlight this idea that if we have a matrix, that we can tell the effect of the matrix on various coordinates by looking at the value we have here. So we notice if we multiply E times some point x, y, z, x is going to go to x. So x will not be changed because the x is being multiplied by the 1 here. So same thing for y and for z. So that's pretty straightforward. We know that the identity has to take the point x, y, z to the point x, y, z. It's not terribly interesting. Well, let's look at what happens with C2. We'll look at the effect of C2, and then we'll see something kind of interesting here that happens. So we're just going to concentrate on C2. And again, we can have this act on some generic point, x, y, and z. And for the time being, we're just going to concentrate on what it does to x. Okay. So if we multiply the first row times the first column, we get that the effect is going to transform x to minus x. And for the time being, we're not even going to worry about what happens with the rest of the molecule, because the other rows of C2 are going to cause an effect on y and z, but they're not going to affect x. So we notice that the effect of C2 takes x and transforms it into minus x. Essentially changes the sign of x. Okay, so we can see the effect of this particular operation just on x. We know already that for the identity, if the identity takes x and sends it to just ordinary x, positive x. So now we want to look at the other two mirrors and see what their effect is simply on x itself. Our first of these will be sigma xz. So recall, this is going to be 1, 0, 0, 0, minus 1, 0, 0, 0, 1. And we have act on the point x, y, z. And again, if we use the process of matrix multiplication, we see that the effect is, if we do the whole thing, we get that x goes to x, y goes to minus y, and z goes to positive z. But if we just concentrate on the effect on x itself, then we notice that sigma xz, when it acts on x, sends it to positive x. Okay. Last but not least, we can look at the sigma yz. Sigma yz here. And then we make the appropriate changes in the matrix. So now that the entries are going to be minus 1, 1, and 1, and the overall effect on a generic point, xyz, is going to send it xyz to minus x, y, and z. So what this really tells us, if we're getting down to the nitty-gritty of it, is the effect of this particular mirror on x is to send x to minus x. Let me just erase this and then we'll tabulate this effect here. So we see that starting with the 3x3 matrices, I can distill the effect on the x coordinate itself. Instead of using a 3x3 matrix, all I really need is a number. It's because I noticed that for the identity, the effect on x is merely to multiply it by a plus 1. Just kind of write this. So it's kind of like plus 1 times x. So instead of using a 3x3 matrix, I only need a 1x1 matrix, which we normally call a number, to tell me everything I need to know about that effect. As far as the C2 rotation, it takes x into minus x. So the effect is of multiplying it by minus 1. So instead of being a 3x3 matrix, I merely need a 1x1 matrix, which is the number minus 1. For sigma xz, it turns x to x. That's the equivalent of multiplying by 1, a 1 by 1 matrix, which is the number 1. And then for sigma yz, it turns x into minus x, so this is minus 1. These matrices that we have, which are essentially just numbers now, so we've gone from a 3 by 3 to a 1 by 1 matrix, a number. These particular entries are called characters. So the character, it kind of distills the effect of the overall symmetry operation on one of the particular coordinates. So we see that the characters that correspond to these matrices with regard to x are 1, minus 1, 1, and minus 1. And we're going to be very interested in these characters, and we're also going to be interested in how many different sets of matrices can we develop for the symmetry operations. How many different sets of matrices that will follow the multiplication rules and the properties of the symmetry operations as we know them for the group. And the properties of the symmetry operations as we know them for the group. Now let us continue with the effects on the y coordinate. So for E, we recall that we can write the E matrix like this. And we'll allow it to act on a generic point x, y, z. And again, we get the point x, y, z back. So I see that as far as the y coordinate is concerned, E takes y and transforms it into y. So this is the equivalent of multiplying by a plus 1. Now let me see what happens with the C2 operation. So our C2, as we recall, is minus 1, 0, 0, 0, minus 1, 0, 0, 0, 1. We're going to allow it to act on the point x, y, z. Really just concerned with the y part at this point, but it's not bad practice to see what this does. We get minus x, minus y, and z. So we notice that the effect of C2 on the y coordinate, so you're actually an operator on it, is to transform y into minus y. And we notice that that is the equivalent of merely multiplying the y coordinate by minus 1. Now for a small bit of terminology. When we have a situation where the effect of the operation on a coordinate is to multiply it by plus 1, we say that this is symmetric. You know, we're talking about symmetry in general, but this is, when we say it's symmetric, means that the character is a positive 1. So the effect of the operation is the equivalent of multiplying by plus 1. We say that the operation is symmetric. If we have a situation where it transforms it into its opposite, essentially it's multiplying by minus 1, we have a minus 1 character. We say that the operation is anti-symmetric. So we can recognize symmetric versus anti-symmetric operations in that the symmetric operations have a plus 1 character and the anti-symmetric operations have a minus 1 character. So we can continue. We have sigma xz. And we're interested in the effect on the y coordinate. No, right there. Okay, let's write the whole matrix. And it's going to act on the point x, y, z. So we're going to get x minus y and z. So what is the overall effect of that thing? Well, the overall effect is to transform y into minus y. So therefore, that's the equivalent of multiplying by minus 1. So this tells us that the sigma xz mirror is anti-symmetric with respect to the y coordinate, and that the character for the operation for the y function is going to be -1. Last but not least, sigma yz and try to see what's coming. We're going to have this act on a generic point xyz, and we get the point -x, y, and z. Restricting our attention simply to the y coordinate, we notice that in this case that sigma yz acting on y transforms it, so we go y to y, and this is just the same as multiplying by a +1. So in this case, we have that the sigma yz mirror is symmetric with respect to the y coordinate, and the character is a +1. Now, these coordinates can be thought of in a more generic sense, so we can use x, y, and z as the coordinates of a particular point that we act on, but these also act as what we call basis functions. So if we have any particular property of our molecule which depends upon the x, y, or z coordinates, we can treat each of these as an individual basis function. And we have lots more of these that are going to come up later on. So these are linear because they're powers of the first power of x, y, or z. And we'll see later on that we can have basis functions. We can have functions that the symmetry operation is going to act upon that are quadratic and cubic and various other things. And those particular basis functions, in addition to giving us some insight into the symmetry operation, how it acts and how it transforms a point, we'll also see how it transforms chemical properties, and the individual basis functions will actually tell us about such things as molecular vibrations and molecular orbitals. So we'll see later on that these basis functions have a much wider implication than just simply as referencing the coordinates of a particular point. Now we'd like to go through and see the effect on the z coordinate, the z basis function. So again, we start with our identity operation E. And the effect on a generic xyz point. And we see it's going to give us xyz. That's not a surprise because it's the identity. But for our purposes, what we want to notice is merely the effect on the z coordinate. It's going to take z and transform it into z. So one way to write that is that the effect of E on z is merely to give us z. And that is the equivalent of multiplying z by a +1. +1, sorry. +1. So we see that the identity operation is symmetric with respect to z. In fact, we'll find that the identity is, as we might suspect, is symmetric with any basis function we want to come up with. So it's always going to give us a positive answer. So our second symmetry operation is the C2. -1, 0, 0, 0, -1, 0, 0, 0, 1. And we look at its effect upon a generic point of the molecule. And we see that in this case we get -x, -y, z. So this shows us that C2 is going to take the z basis function and send it to the z basis function. It's unchanged, which is the equivalent of multiplying by a +1. So we notice that the C2 symmetry operation is symmetric with respect to the z coordinate or to the z basis function. And our next symmetry operation is going to be sigma xz. So this is, again, another one of our vertical mirrors. 1, 0, 0, 0, minus 1, 0, 0, 0, 1. And we have it act upon xyz. And we notice the effect is to give us x minus y, z. So this tells us, if we just concentrate on the effect on the z coordinate, it takes z to z. So sigma xz transforms z into z, which is the equivalent of multiplying by the number 1. So we see that with respect to the z-axis, this particular sigma v is going to be symmetric because the character is a +1. And our last symmetry operation, yeah, sigma yz minus 1, 0, 0, 0, 1, 0, 0, 0, 1. On the point xyz. And it's going to transform it to the point minus x, y, z. So this tells us that the effect of sigma yz on z is merely to transform it into z. This is the equivalent of multiplying it by the number 1. So we say that in this case, the character is a +1. And we notice that each of these numbers, they're characters, but they're also representations. Or rather, the entire set of these characters forms a representation, just as this particular set of 3 by 3 matrices constitutes a representation of the group. Now, it turns out that there are two different types of representations. There are reducible representations, and there are irreducible representations. So just kind of show reducible. And then irreducible. It turns out that we can construct an infinite number of reducible representations, but that the number of irreducible representations is fixed for a particular group. And we're particularly interested in these irreducible representations because there's only a certain number of them, and then we can take any reducible representation and convert it into a linear combination of irreducible representations. So it turns out that our irreducible representations are sort of our building blocks. And we can even think of them as a building block of the group because in certain ways the representations for the group act like a group themselves. So we're going to look at these irreducible representations and how they are related to the characters. If you look at the back of any inorganic chemistry textbook, or in the back of most physical chemistry textbook, you will find so-called character tables. Character tables. And you will notice that there's a different character table for each point group that's listed. So we're going to look at the character table for the point group C2V, which is the group that we've been looking at. Typically in the upper left-hand corner, they'll put the name of the group, so that's C2V. And then across the top, you'll see a list of symmetry operations of the group. Now across the top, I'll list all the symmetry operations of the group. You'll notice there are a number of columns. So the number of columns is one column for each class. Now in C2V, each symmetry operation belongs to its own class, but that is often not true. Sometimes we have several symmetry operations that are all in the same class, and we'll mention later on how we know when things are in a class or not. For the time being, we notice that we have 4 classes. And we also know that we have 4 symmetry operations. Since we have 4 symmetry operations, that tells us the order of the group, and the symbol that we use for that is generally a small h. So the order of the group is 4 for the point group C2V. Next, along the left-hand side, we see a combination of letters and numbers. So we see A1, A2, B1, and B2. These particular rows, so each column is a class of the group. Each row is an irreducible representation. We'll see later on what the significance of these A1, A2 business is, but the important thing for the time being is that we have 4 irreducible representations for the point group C2V. These are the only irreducible representations that there are. That includes all of them. We will notice a rule that's always true, that there will always be exactly as many irreducible representations as there are classes of our group, such that every character table will therefore be a square, because they'll have the same number of rows and the same number of columns. And then we have a series of numbers which are written in the rows and columns. Now to the right-hand side, we typically have a listing of so-called basis functions. I'll just put them down for a second. So we have our basis functions, and in this particular case, we'll see things like z. I'm leaving out a number of the basis functions because we won't get to them yet, so I'm only going to put in the basis functions that we're going to talk about in the near future. But the important thing is, if I ignore the bases for the time being and just concentrate on the columns for the classes and the rows for the irreducible representations, that we have the same number of irreducible representations as we do classes. Each of the numbers that's listed at the intersection of a row and a column is a character. So as we had noticed in the very last example that we had done, where we were looking at the effect on the z-axis, I noticed that the character for the E operation was 1, for C2 was 1, for sigma v x z was 1, and for sigma v y z was also 1. That was the last example we had done. So here's where those numbers came from if I was trying to derive the character table from the set of 3 by 3 matrices. So that's where these numbers come from. I haven't written the plus in just for clarity, but plus 1 equals 1. Notice that when we had done the x coordinate, the x basis function, that the character I had found was a plus 1 for E, but was a minus 1 for C2. For sigma xz was a plus 1, and for sigma v yz was a minus 1. So that is where these numbers came from. And we had done in our derivation, we looked at the effect upon the x coordinate, so that gave us the 3rd row. The effect on the y coordinate was the 4th row. And then the effect on the z coordinate was the 1st row. We haven't yet seen where the 2nd row comes from, but bear with me. We will see that shortly. Now, one of the things to mention about the order of the irreducible representations is that we might expect that they would go in the order of x, y, and z. So you might wonder, well, why is the z basis function irreducible representation the first in the table? Well, this one, there's always one representation, which consists entirely of characters that are plus 1. So it's 1, 1, 1, 1, 1, 1. So we can always write from memory, without even looking at the table, what the first row of any character table should be. We just put the number 1 in. So this is a special representation. And it goes by different names. So it's called A1 here. It's called similar things elsewhere. And this is the totally symmetric representation. Totally symmetric representation. Sometimes it's called the identity representation. So it's, while all of the irreducible representations are created equal, some irreducible representations are more equal than others. And among those, the most equal, the most important of the equal irreducible representations is this totally symmetric representation. And we'll see shortly some of the reasons why it's so important. But the important thing to keep track of is that we only have a finite number of irreducible representations, and that the number of irreducible representations is exactly equal to the number of classes for our point group.